All right, let's discuss molecular geometry and bonding theory. The subject of molecular geometry deals with the shapes of molecules. Recall that our Lewis structure is a two-dimensional representation of a molecular ion. Its intent is to show how the valence electrons of atoms are distributed in the molecule. A Lewis structure does not necessarily have to depict the actual shape of the molecular ion, but we can use it to deduce the actual shape. Since atoms are always in motion, when we talk about the shapes of molecules or ions, we mean the shape based on the average location of the atoms. A description of the geometry of a molecule or ion involves the positions of all the atoms in the molecule relative to each other, which includes the parameters of bond angles and bond lengths. In a Lewis structure, two atoms are joined by a line. When more than two atoms are joined together, these lines intersect at a given central atom and form angles with each other. These angles are called bond angles. For example, in ammonia here, we have two hydrogen atoms joined, intersecting at the central atom, and it forms a bond angle of 107 degrees. The line or bond joining two atoms connects the nuclei of the two atoms, with the length or distance between these two nuclei being called the bond length. So when we talk about bond length, we're talking about the distance between the two nuclei, in this case of hydrogen and nitrogen. The bond angles and bond lengths of a molecule or ion dictate the particular geometry of a species. Lewis structures are two-dimensional representations of the molecule, but because molecules are three-dimensional, a picture of the molecular geometry must convey information about the third dimension as well. Our drawing surface is flat. Therefore, we use a projection which includes dashed line wedges for bonds to indicate the three-dimensional molecule. Bonds are represented as ordinary lines if they are in the plane of the paper, solid wedges if they are pointing out of the paper, dash wedges or dashed lines if they are pointing into the paper. Here's an example. Basically, if we have this wedge, we're trying to say that that's coming forward out of the plane of the page. If we do the dash line, then we're saying that's going backwards into the plane of the page. If we have a solid line, then we're saying that's in the plane of the page. So this particular drawing, we're saying that this line and this line, whatever atoms are attached to those, are in the plane of the page. This one's coming out of the page, and that one's going back into the page. Ammonia has a geometry that is trigonal bipyramid. Looks like a pyramid with nitrogen at the top and hydrogen at the base of the three corners. If the nitrogen atom is in the plane of the paper, one 3D arrangement could have two hydrogen atoms pointing back into the paper, with the third pointing out of the paper, or vice versa. So basically what we're saying here is, in this particular arrangement, what we have is a pyramid, and you have three hydrogens at the corner. Get this hydrogen coming out at you, and these other two hydrogens going into the plane of the board. Now we could have also drawn this just as well, with two hydrogens coming out of the board, and then one hydrogen going into the board with your lone pair at the top. So that would have had the two hydrogens pointing directly at you, one going straight back from you. To determine the shape of a molecule based on the bond angles and bond length, we use a simple theory called VSEPR, theory, which is valence shell electron pair repulsion theory. The basic idea behind VSEPR is that regions of high electron density, meaning electron groups around each atom in a molecule, tend to be oriented as far away from one another as possible. Depending on the number of electron groups around the central atom, there will be a particular geometry available that minimizes the electron repelling forces in the molecule. Once we know how the electron groups around an atom are oriented, it becomes easy to imagine the shape of the molecule. Let's take a look at the following example. Okay, I have these two electron density regions. around the atom, the central atom, and I have them here 90 degrees apart, and I have them 180 degrees apart. Which orientation gives the most space between the two negative charges around the central positive charge, the 90 degree or the 180? Obviously, the 180 degree gives the best use of the space and allows the two negative charges to get as far apart as possible, have 180 degrees in both directions. This one has 270 this way, but we have 90 this way, so we're closer there. So the best arrangement would be this one right here, 180 degrees. This means that a central atom that has two electron groups around it will adapt a geometry that is linear in shape. Electron groups will be 180 degrees apart. Let's look at another example. Here I have three electronic groups around the central atom. We have them staged like in a T shape, and then we have it in a Y shape. Which orientation gives the most space between the three negative charges around the central positive charge? Once again, obviously, the shape that has all three negative charges is 120 degrees apart. These are 120, 120, and 120. This gives the best use of space and allows the three negative charges to get as far apart as possible. In this one, you have this 90 degrees, and these are 90 degrees. So they can get more space if they spread out in that Y formation. This means that the central atom that has three electron groups around it will adapt a geometry that is trigonal planar in shape. Electron groups will be 120 degrees apart. Bottom line, depending on the number of electron groups around the central atom, there will be a particular geometry that allows all electron groups to maximize their distance from each other. The first step in figuring out the shape of a molecule is to determine the steric number of atoms that are bonded to at least two other atoms. Steric number refers to the number of electron groups around an atom and gives us information on how these groups will orient relative to each other. To determine the steric number, we must account for the following. A single bond counts as one group. A double bond is counted as one group. A triple bond is counted as one group. A lone pair is counted as one group. Basically, each electron density region, meaning group of electrons between atoms, around an atom counts as one group, and a lone pair counts as one group as well. To determine the steric number, we must first draw the Lewis structure and then count the number of electron groups around an atom. What are the steric numbers for the carbon atoms in the Lewis structure below? Well, looking at them, we see that we have around this carbon one region, a second region, and a third region. It doesn't matter that this is a double bond, that still counts as one region between the atoms. And this carbon has exactly the same. You have three regions around that carbon atom. Both carbons have three electron groups around them, two single bonds and one double bond. So we have three around one carbon, and we also had three around the second carbon. So hence, both have a steric number of 3. Let's look at the next example. We have one region between this carbon and hydrogen, then we have one between the two carbons. Once again, this is a triple bond, but that counts as one region. So this only has 2 for both carbons. Both carbons have 2 electron groups around them, one single and one triple bond. 2 around this carbon and 2 around the other carbon. Steric number in both cases in this example is 2. So both carbons have a steric number of 2. What are the steric numbers for the oxygen and nitrogen atoms in the Lewis structures below? Well, looking at this one, I have around oxygen, we have this one region, another region, that's 2, and I have one above and one below with the lone pairs. So this has 4 regions. The oxygen atom has 4 electron groups around it, 2 single bonds and 2 lone pairs. Since it has 4 regions, the steric number for this is 4. Let's look at the ammonia. You had 3 single bonds and 1 lone pair. So the 3 single bonds are each one region, and in the lone pairs 1 region. So you have 4. The nitrogen atom has 4 electron groups around it, 3 single bonds and 1 lone pair. Therefore, the steric number in this case is 4. Once we have determined the steric number of an atom, we can predict the measure of the angle formed by the electron density sticking out of that atom. However, when the groups on the atom are not identical, we must realize that the bond angles will differ slightly. Bond angles are affected by the type of electron density regions, electron groups, around of the atom. Lone pairs repel other groups more strongly than bonded pairs, and multiple bonds repel more strongly than single bonds. So repellant force interactions are greater in lone pairs. So if you've got a couple of lone pairs, they're going to repel the bonded pairs more and make that bond angle smaller. If you have a lone pair bonded pair, that's going to be less than a lone pair, but that will be greater than a bond pair. So depending on the arrangement, that can cause the angles to get smaller and cause those bond angles to decrease. Many physical properties of molecules are directly related to whether they are polar or nonpolar. The overall polarity of a molecule depends not only on the polarity of its bonds, but also on its geometry. Each polar bond has a bond moment, but each molecule also has an overall molecular dipole moment that is approximately the sum of all its individual bond moments. The vector sum of bond moments must include not only the magnitude of the bond moments, but also their direction. To determine if a molecule is polar or nonpolar requires the examination of the bond moments and their orientations within the geometry of a molecule. If the bond moments are oriented in such a way that it cancels out each other, the molecule is nonpolar. Remember, we discussed this back in the previous chapter. Let's talk about the arrangement of electronic groups about an atom based on steric number. If we're talking about a steric number of 2, meaning 2 groups, we will call the molecular geometry linear. Here's a picture. Okay, basically we're talking about 2 groups around an atom, so they're going to get 180 degrees apart. So the bond angles involved here would be 180 degrees. If we're talking about polarity, assuming that all atoms are the same, you would have your vectors pointing in opposite directions. Therefore, they would cancel out each other. So this would be a nonpolar molecule. The geometry of this involves 2 atoms bonded to the central atom, an AX2 arrangement. Example, CO2, and we covered this one before in the previous chapter. Let's talk about 3 groups, a steric number equal 3. The molecular geometry would be trigonoplanar. So what we're looking at is a planar system, okay, that's kind of in the shape of a Y, but it's trigonal, and all the angles would be 120 degrees apart, okay, and there'd be 128 degrees between each one of those atoms. Polarity in this case, well, the vectors will all be pointing opposite directions, so they would be nonpolar. They will cancel out each other. This involves 3 atoms bonded to a central atom or an AX3 arrangement. Example, the nitrate ion. Basically, you have 3 oxygens around the central atom, all of them about 120 degrees apart. Let's talk about a steric number equal to 3. Molecular geometry bent or angular. So this has the same steric number as the previous one, but in this particular case, there's going to be a lone pair involved as well. So this arrangement looks exactly like the trigonoplanar, except you have a molecule up here at the top on the trigonoplanar. But in this case, you have a lone pair up here instead of a bonded pair. When we're talking about geometry, molecular geometry, we're only worried about the atoms, okay? We're not talking about where the lone pairs are located. So if you look at this, it looks bent, okay, or angular. The angle is going to be, instead of 120, because you get a lone pair, that's going to have more pull, and it's going to push these 2 bonded pairs closer together, so that angle is going to be less than 120 degrees. If you talk about polarity now, you have these 2 vectors that are pointing in one direction, and then you have this lone pair that's a strong pull going in the other. So what you're going to have here, depending on which way these vectors are going, they're not going to cancel no matter what. You're going to end up having an overall net dipole. So this is going to be a polar molecule. Geometry involves two atoms bonded to the central atom which also has a lone pair. So this is an AX2E arrangement. Example, NO2 minus. In this case, you have your vectors. You have your pull of your vectors going out, but the lone pair is stronger pull going up. So therefore, this is going to end up being a net dipole. Your angle is not 120. That lone pair is going to take more room, so these oxygens are going to get a little closer, so it's 114.5 degrees. Let's talk about steric number equal 4, geometry tetrahedral. Here's the example. Basically what you have is a little pyramid. You got this triangle base like a pyramid, and then an atom at the top. Okay, it's called a tetrahedral arrangement. Bond angles are all 109.5 degrees apart. In this case, the vectors are going to cancel out, so they could have moments, but the net sum is going to be 0. Therefore, this is a non-polar molecule. Geometry involves 4 atoms bonded to the central atom, an AX4 arrangement. Example, methane. You have your carbon in the middle, and you got one hydrogen in the plane this way, one plane in the plane this way. This one going into the paper, this one coming out. So your vectors will be all pointing, in this case, inward, all canceling out. Steric number equal 4, same one as the one before, except in this case it's called a trigonal pyramid. A trigonal pyramid. A pyramidal. This is a case where we have a lone pair. So you have the same arrangement as before, this pyramid, but instead of an atom at the top, you're going to have a lone pair. The angles are not going to be 109.5 anymore. They're going to be less than that. That lone pair at the top is going to end up pushing down those atoms closer together. This is going to be polar because you have that lone pair, which is a stronger pull than the other one, so there will be a net dipole, and this will be a polar molecule. Geometry involves 3 atoms bonded to the central atom, which has a lone pair. So this is an AX3E arrangement. Example, ammonia. You have your dipoles in this particular case of pointing in toward that nitrogen, and you have that large one with the lone pair, so this is a very polar molecule. It has a net dipole. Here's another steric number equal to 4, which is going to end up having 2 lone pairs on it. This is going to be referred to as bent or angular. So what we're saying here is you have this arrangement up here, and we're going to add another lone pair at one of these 3 sites. So once again, you have an angular or bent shape. So you have the 2 bonded atoms and 2 lone pairs. Bonded angles are going to be less than 109.5. Those lone pairs are going to push this angle smaller. And once again, it's still going to be polar. You're still going to have a net dipole. This involves 2 atoms bonded to the central atom and 2 lone pairs. This is an AX2E2 arrangement. Example, water is an example. You have your hydrogen atoms and you have 2 lone pairs. So you're going to have your vectors pointing toward the oxygens from the hydrogens, and then the 2 lone pairs pulling out. So that's all of it summing in the same direction. So water is a very polar molecule. What we're saying about the vectors is you have your dipole moment. You may recall this from a previous chapter. It's going from the positive end pointing to the negative end, so it's pointing toward those oxygens. And you also have they're pointing out toward those lone pairs. So all these are in essence pointing in the same direction or summing up for a large dipole moment. Let's talk about steric number equal 5. This is a trigonal bipyramid. So by the name, you're looking at 2 pyramids. So in essence, we have 1 pyramid up and 1 pyramid down. You got your planar in the middle, and then 1 up, 1 down, making the 2 pyramids. In this case, you have 90 degree, 120, and 180 degree angles. Okay, you got 90 between these 2. You got 120 between those in the equatorial, and then you have 180 between the top electron and the bottom one. In this case, your three equatorial dipole moments are going to cancel out. They're all pulling in opposite directions. And then you have your upper and bottom one pulling in opposite directions, so everything cancels out. So this is a nonpolar molecule. This geometry involves 5 atoms bonded to the central atom, an AX5. Example, phosphorus pentafluoride. In this particular one, you got the 2 fluorines in the plane of the paper. You got this fluorine in the plane of the paper. Then this fluorine's going into the paper, and this fluorine's coming out, with all the ones in the middle 120 degrees apart, and then 190 degrees between those F's. All right, let's look at steric number equal 5, but in this case, we have a lone pair. This geometry is going to be seesaw. Basically, it is this trigonal bipyramid rotated on its side. That way you can see the seesaw and where the name came from easier. But what we have is a lone pair right here. Okay, that's where it's going to want to be located, because that lone pair wants to go where it has the most room. In this case, it's going to be right in this location. Bond angles, you're going to have your 100, they're going to be less than in all the bond angle cases, because that lone pair is going to take more room and push down. So this 180 degree is now going to be less than 180. This 120 is going to be less than 120, as well as this 90 is going to be less than 90. Everything's going to be kind of moving in toward each other because of that lone pair. Now, what's going to happen, since I have this lone pair, it's going to end up being a polar molecule. I'm going to have an excess. Anytime I got one lone pair, I'm going to have a polar molecule, because it's not going to cancel out with anything. The top ones are going to cancel each other out, but these back ones, doesn't matter if the dipole's going in or out, they're either going to be additive with that lone pair, or they're not going to be as large. So it's going to end up being a polar molecule. This involves 4 atoms bonded to the central atom, which has one lone pair. This is an AX4E example. This is sulfur tetrafluoride. You can see I have my lone pair in the equatorial. That's where it's going to want to go. And I have my fluorine going into the board and out of the board. This is going to be about 101.6 degrees between these fluorides instead of 120. This is also steric number 5, but we have 2 lone pairs. This is going to be T-shaped. Okay, it looks like a T. Basically, we got our 2 lone pairs. Okay, our 2 lone pairs are running kind of like that in the equatorial. Okay, so it's going on that equatorial side. This looks like a T. That's where the T shape comes from, except that it's really not a T shape. It's going to be a distorted T shape, because the angle is going to be less than 90 and less 180. Since you have these lone pairs sticking out like here, that's going to push these angles down and make that less than 180 degrees and less than 120. The lone pairs are gonna we're not gonna the net dipole moment's gonna be one. They're not gonna cancel out, so therefore this is gonna be a polar molecule. This is 3 atoms bonded to the central atom, which has 2 lone pairs, an AX3E2 arrangement. Example, ClF3. We have the 2 fluorides at the axial, and then we got 1 fluoride on the equatorial, and then we got the 2 lone pairs on the equatorial. You can see the angle on this is about 87 degrees instead of 90. Okay, once again, another steric number equal 5, but in this case it's going to be a linear. Now I got 3 lone pairs. All 3 are going to be on the equatorial. So all 3 are going to be on that equatorial. So that leaves us with a linear molecule arrangement. Got the 2 atoms, the other 3 are lone pairs. Bond angle will be 180, because all those lone pairs are going to repel each other, and basically it's going to have no effect on the bond angle there. And those lone pairs are going to cancel each other, since they're all around the equatorial, pulling in opposite directions. And then your Bonded pairs are going to be pulling in opposite directions, so this is going to be a nonpolar molecule. This involves two bonded atoms with three lone pairs, an AX2E3 arrangement. Example, I3 minus. Okay, I end up with my three lone pairs on the equatorial and then my eyes on the axial. So we end up with our linear arrangement. We move on to steric number equals 6. This is called an octahedral. Basically, you have a square planar center. Okay, you see I got this crisscross, and then one up and one down. That's an octahedral. Angles, you have 90 degrees, and then you have 180s. Oh, as for polarity, the bonds are going to, bonded atoms are going to cancel across from each other, so everything cancels out. So you get a net dipole of 0, so it's nonpolar. This has 6 atoms bonded to the central atom. This is an A6 arrangement. Example, sulfur hexafluoride. So in this case, I got a fluoride up and down in the plane of the paper. I got 2 fluorides going into the plane of the paper and 2 fluorides coming out of the plane of the paper. Okay, steric number equals 6. Now let's throw in a lone pair. That's going to end up being square pyramidal. Basically, it's going to prefer one of these actual positions. That's where it's got the most room. So therefore, one of these will be a lone pair. So then if you're just looking at the atoms, you got a square and you got a pyramid. Square pyramidal. The lone pair is at the bottom. Bond angles are going to be less than 90 because you got that lone pair. It's going to push, since you got the lone pair down here, it's going to push all these atoms up some. What's going to make the angle less than 90. Polarity. For polarity, basically they're going to all cancel out up here, but you got this lone pair. If it's got a single lone pair, it's going to have a net dipole, so it ends up being a polar molecule. Geometry involves 5 atoms bonded to the central atom, which has 1 lone pair, which is AX5E. Example, bromine pentafluoride. So I have my 4 fluorines in the planar, 1 fluorine at the axial, and then we have the lone pair across from it. Steric number equals 6. We're going to have 2 lone pairs now. What's going to happen is it's going to be at the top and bottom, the actual positions, and leaving the 4 atoms in the plane. So it's going to be a square planar. That's what it looks like, a square plane. So you basically got your middle with your atoms, and then your lone pair up and your lone pair down. So you got a lone pair up and a lone pair down. So you're going to have 90 degrees and 180s. It's not going to be less than because those lone pairs are going to cancel each other out, so the atoms will stay put. For polarity, what's going to happen is we're going to cancel across these atoms, and you're going to cancel the lone pairs. Therefore, it's going to be nonpolar. Geometry involves 4 atoms bonded to the central atom, which has 2 lone pairs. This is an AX4E2 arrangement. Example, xenon tetrafluoride. Got my fluorides, got 2 coming out, 2 going in, and I have 1 lone pair up, 1 lone pair down. Now I could have tilted this to the side and put all 4 fluorines in the plane of the paper, drew those all straight solid lines, and then put 1 lone pair coming out, 1 lone pair going in. Or if you're drawing the molecular geometry, you don't even bother to put the lone pairs. Note, there are other molecular geometries with our steric number equal to 6. AX3E3, which is T-shaped. AX2E4, which is linear. As well as other molecular geometries that are greater than steric number equals 6. But we will not cover these in this course. Now, I have all these geometries and the polarity and all that in a table at the end of this PowerPoint presentation, which I'll show you when we get there. Kind of put it in one spot that you can see it all and kind of see what you have to memorize to be able to determine the shapes. The VSEPR model provides a way to predict molecular shapes but says nothing about the electronic nature of covalent bonds. To describe bonding, the valence bond theory, or VB model, was developed. The VB model provides an orbital picture of how electron pairs are shared in a covalent bond. Covalent bond results when two atoms approach each other closely enough so that a singly occupied valence orbital on one atom overlaps a singly occupied valence orbital on another atom. These paired electrons located within the overlapping orbitals are attracted to the nuclei of both atoms, forming a covalent bond between the atoms. For example, the hydrogen-hydrogen bond in H2 results from an overlap of two singularly occupied hydrogen 1s orbitals. So you have a 1s orbital of hydrogen and another 1s orbital from a different hydrogen. What happens is they overlap and they share those electrons between them. According to this model, it would seem that for an atom to form a covalent bond, it must have an unpaired electron, as we showed in the previous example. I have one electron here from my valence electrons, one here, and then they come together and share that orbital. Now, what happens if I have a full octet? How does it bond? Well, we have things that have full octets that tend to bond, so we need to come up with another theory to explain that. So according to this model, it would be seen that for an atom to form a covalent bond, it must have an unpaired electron. However, experience tells us that this is not true. To adapt the valence bond model to include bonding between atoms with no unpaired electrons, the hybridization model was developed. This model accounts for the experimental evidence about molecular structure much better than the simple overlap valence bond model. The hybridization model modifies the description of the atomic orbital when they overlap to form bonds. Basically, what we're saying here is that the hybridization model, that we form new orbitals that are there for better overlapping. In this model, we do not describe the orbitals by using simple s and p orbitals, but instead we use hybrid orbitals that are now newly formed, which are combination orbitals formed by the mixing of simple atomic orbitals. The number of hybrid orbitals formed is equal to the number of atomic orbitals mixed. Although it appears that hybrid orbitals are nothing more than a different way of describing electrons, there is an underlying physical reality that we are actually describing. The new orbitals are more suited for forming bonds. A bond is a result of an overlap of two orbitals, one from each atom of the bond. The better the overlap, the stronger the bond. Pure atomic orbitals are quite symmetrical, resulting in a relatively little overlap before their nuclei approach close enough to begin repelling each other. Hybrid orbitals are less symmetrical than unhybridized ones, resulting in more effective overlap and stronger bonding. The formation of beryllium hydride molecule can be explained using the hybridization model. It is assumed that as two hydrogen atoms approach beryllium, the atomic orbitals of the beryllium atom undergo a significant change. A 2s orbital is mixed or hybridized with a 2p orbital to form two new sp hybrid orbitals that will have better overlap, meaning bonding, with the 1s orbital of the hydrogen. So what's happening is we have a 2s orbital and a 2p basically coming together and form two new orbitals that we're going to refer to as sp orbital, which is totally different than the s or the p, and it's suited for better overlap and bonding with other orbitals. So you have one s orbital and one p that now form two sp orbitals. The next slide describes the process using an orbital diagram. So you have your Lewis dot structure here of your beryllium hydride. Beryllium is a 1s2, 2s2. So if you look at its ground state electron configuration, it's completely filled. I have 2 in the 1s and 2 in the 2s. So why would it bond with something else? Well, what's going to happen is Beryllium does not have unpaired electrons. Therefore, it must promote an electron to a p orbital to form the valence state before bonding will occur. So what has happened is the 2 electrons in my 2s promotes one of those electrons to the 2px level. So first it promotes an electron to the p orbital, and then we call this the valence state or excited state. Now this 2s and this 2px are still not good for overlapping, so what they do is they rearrange the hybridization process. The 2s and 2p orbitals are mixed so that they form 2 hybrid mixed orbitals that are better suited for overlapping with the 1s orbitals of hydrogen. So this 2s and 2px form 2 new orbitals called sps, totally different, that are better for overlapping. So then I have my 1 electron in each one of those, and is this sp orbital that overlaps with the hydrogen. So you have your hydrogen s, and you have an sp from beryllium that basically overlap and share those electrons. And the same thing's happening on the other side. You got another sp that's overlapping with an s on the other hydrogen for their electrons. A similar process occurs for all atoms bonded to molecules. They undergo hybridization to form new orbitals that allow for better overlapping and bonding. The bonding in carbon might be explained as follows. You have CH4, methane. It has 2s2, 2p2 as its valence electrons. That means I have 2 in the s's and 1 in the px and 1 in py. Well, what's going to happen, this is the ground state, so to be better situated for better bonding, it's going to promote one of those electrons to the third pz orientation. That'll give me 4 electrons, each singly by themselves in the orbitals. So I have 4 unpaired electrons are formed as an electron from the 2s orbital is promoted, excited to the vacant 2p orbital to form the valence state. However, it's still not in a good overlapping arrangement, so these 4 orbitals, the 2s, the 2px, 2py, 2pz, are going to have to undergo hybridization. So here's your energy diagram. You have your 1s, which is not involved. You have your valence electrons. You have your 2s, which is 1 up, 1 down, and then you have 2p's. This 1 in the 2s has to be promoted up to the 2p level, and then after it gets excited, we're going to have to undergo some hybridization of these 4 orbitals to form new orbitals that are better suited for hybridization. For overlap. So this is its valence excited state. This promotion would give 4 unpaired electrons available for bonding. 1 bond on carbon would form using the 2s orbital, while the other 3 bonds would use the 2p orbitals. However, this does not explain the fact that the 4 bonds in methane appear to be identical and not a single 2s and 3 2p orbitals. They all look exactly alike. The hybridization model assumes that the 4 available atomic orbitals in carbon combine to make 4 equivalent hybrid orbitals. The 2s, 2px, 2py, 2pz mix to form 4 new equivalent, what we're going to call sp3 orbitals, and we get the sp3 name from the s involving 3 p's, that's where it comes from, that are better suited for overlapping and bonding and containing an unpaired electron. So instead of having an 2s and 3 2p's, we formed 4 new ones that we call sp3 and have each one of those have 1 electron. Hybrid orbitals are orbitals used to describe bonding that are obtained by taking combinations of atomic orbitals of an isolated atom. In the carbon case, a set of hybrids are constructed from 1s orbital and 3p orbitals, so they are called sp3 hybrid orbitals. The 4 sp3 hybrid orbitals take the shape of a tetrahedron. Each carbon-hydrogen covalent bond results from an overlap between a singly occupied hydrogen 1s orbital with a singularly occupied carbon sp3 hybrid orbital. So here's your CH4, your methane, and what we're saying here is each one of these hydrogens is an s orbital, and that bond between that carbon and that hydrogen is an overlap between that s and an sp3. So each one of those carbons is an sp3 orbital overlapping with that s, forming the bond. So we can represent this hybridization of carbon and methane as follows. You have your excited state. Remember, we took this one electron and promoted it up. Okay, we had one electron here that we promoted up to the 2p level. Now we have the hybridization occurs. So basically these 2s and 2p's, those four orbitals, form four new orbitals, which we refer to as sp3, and now they're all suited for bonding. So you have your sp3s, okay, of your carbon, and then you have your hydrogen, which is a 1s. Those come and combine with those sp3s and form that carbon-hydrogen bond. Okay, forms that carbon-hydrogen bond by that overlap between the sp3 and the s orbital and hydrogen. In general, we can correlate the steric number to the hybridization of an atom. There is a relationship between the type of the hybrid orbitals and the geometric arrangement of those orbitals. So it's fairly easy to determine the hybridization. If you know the steric number, you can easily determine the hybridization. If the steric number is 2, the hybridization is sp. If the steric number is 3, the hybridization is sp2. If the steric number is 4, the hybridization is sp3. 5, sp3d. 6, sp3d2. You can memorize them, or you can see there's a real pattern here. Basically, you have an s, one s every time, and then you increase p, p2, p3, until you finish with the number of orbitals in p. Remember, there's 3 orbitals in p. Then you start the d's, d, d2, d3, etc. All right, what are the molecular geometry, angles between bonded atoms, the hybridization, and the polarity of xenon difluoride? Well, first, you have to draw the Lewis dot structure. So you need to figure out how many electrons are available. So with xenon, okay, we have 8, and fluorine you have 7. You got 2 7s, that's 14 plus the 8, there's 22 electrons available. So you have your xenon as your central atom and 2 fluorides. If you do your Lewis dot structure following the rules we did in Chapter 9, you would complete your octets around the fluorines, which would give you 16. Subtract that from your 22, which means I got 6 left. So you would put that on your central atom, which means now you got 2, 4, 6, 8, 10 around it, but that's okay because this is one with those d orbitals that allows it to expand. So now I know my Lewis dot structure. Now what I want to do is figure out what is the steric number. How do we do that? We count the number of electron density regions around the central atom. And we count double bonds and triple bonds as one region, and lone pairs are one region. So in this case, I have 1, 2, 3, 4, 5 regions. So this is a steric number 5. So this means it's going to be part of that trigonal bipyramid classification. But since it has lone pairs, you're going to have to go down that steric number 5 down the list until you figure it out. Well, looking at the shape, you can easily see what's going to happen here is if these are my lone pairs and all I'm looking at is the bonding pairs for my geometry, what's that look like? Linear. So the molecular geometry for Sn equal 5 with 2 bonded pairs and 3 lone pairs is linear. The angle between the bonded pairs, well, since these are all lone pairs, they're repelling each other the same, so that's not going to affect the bond angle. So the only bond angle we have is the 180 degrees. So the angle between the bonded pairs is 180 degrees. What about hybridization? Well, since it's Sn equal 5, we know you got S, P1, P2, P3. That's 4, so I'm going to have a D. So sp3d. Since this is the Sn equal 5, the hybridization is sp3d. So you either memorize it or figure it out. Remember, there's maximum 1 S, 3 P's, and then D. Polarity. Well, your lone pairs, you have your vectors pointing out for your lone pairs, but they're all pointing in opposite directions, so they're canceling out each other, as well as the polarity is pointing out to the fluorines, so they're canceling out each other. So everything cancels out, so there's no net dipole. So this ends up being a non-polar molecule. All dipoles cancel out each other. All 3 lone pairs pull out from the center, while the 2 bonded pairs pull in opposite directions. Therefore, this is a non-polar molecule. What are the molecular geometry, angles between bonded atoms, and hybridization and polarity of ammonia? Well, you count your valence electrons. Nitrogen has 5, hydrogen 1. You got 3 of those. That's a total of 8 electrons. So you have to draw your Lewis dot structure. So you have your 2, 2, 2 for your hydrogens. You got 2 left over, so you put it on the central atom. Therefore, it has 8. So here's your arrangement. Next, we've got to look for the steric number. So around nitrogen, you have 1, 2, 3, 4 regions. So this is a steric number equal 4, which is the tetrahedral class, but since it has 1 lone pair, it's going to end up being called pyramidal. So we see we got 4 electronic groups around, steric number equal 4. Molecular geometry Sn equal 4 with 3 bonded atoms and 1 lone pair is your trigonal bipyramid. Okay, let's talk about angles between bonded atoms. This typically would be 109.5, but since you got that lone pair, it's going to push on these more. So this ends up being less than 109.5. So angles between the bonded pairs are less than 109.5. The lone pair causes the angles on the bonded pairs to decrease. It's going to push down on these. So that's going to push it down, making that angle less than 109.5. Hybridization, since you have a steric number of 4, you can have S, P1, 2, 3. So it's a sp3. And polarity, well, you're going to have your vectors pointing toward the nitrogens, and then you got a vector pointing up to the lone pair, so they're all additive, so it ends up being a very polar molecule. All dipoles are additive, lone pair pulls out, and all 3 bonded pairs pull toward the center, resulting in the overall dipole moment for the molecule. Therefore, this is a polar molecule. Here's the table I told you about. Pretty much I have everything in order now, so you can see the steric number, 2, 3, 4. I have the angles associated with that steric number, the hybridization, and the geometry. So you can see with steric number 2, we're going to have a linear arrangement, and then we talk about the polarity is nonpolar because what you have here is your vectors pulling in opposite directions. Here's steric number equal 3. We know the angles are 120. Hybridization sp2, trigonal planar. And we're saying in this case that there's no, the polarity is cancels out, dipoles cancel out. So nonpolar. Then we say, well, what if we have any lone pairs? Well, I got 1 lone pair. We're saying that the angles get smaller. They go down. And that lone pair is going to have extreme pull on it, so it's going to be a polar molecule. This is angular event. Next, you had the steric number 4, which is 109.5, which is your tetrahedral class. So in this case, you have all your vectors pointing in opposite directions, canceling out, so it's nonpolar. If you put a lone pair on there, then it goes less than 109.5. Hybridization sp3. And these angles get smaller. And since you got that lone pair, it's going to end up being polar. If you got 2 lone pairs, it's going to be less than 109.5, still sp3. We're going to call that bent or angular. We're only looking at the atoms when we're talking about the geometry. And this is all going to be additive, so this is going to be yes polar. So I suggest you kind of learn this thing so when you get your steric number, you know how many lone pairs and what the shape should be. If you memorize the basic shape and then know where to put the lone pairs, you can look at the shape and figure out what the name of it is for the most part. Steric number 5, we talked about 90, 120, and 180s. Trigonal bipyramid, and we say everything cancels. All the vectors cancel across the equatorial and then also on the axial. Then you have one lone pair. We got less than 90, 120, 180 because this lone pair is going to push these things closer. Okay, so this pushes the angle closer, those lone pairs, and it's less than the degree expected. And then what about polarity? Well, I got one lone pair, so it's going to be polar. Hybridization, sp3d. Now, what if I put two lone pairs? They're going to have to be in the equatorial. And then what's going to happen is your angles are still going to be less because there's going to be more pushed on it. There's going to be a T shape, sometimes referred to as distorted T, because these angles are going to be smaller. And you're going to have a polar molecule. What if you have three lone pairs? Well, that's all on the equatorial, so all you have is your axial eyes at the top and bottom in this particular case. So then sp3d, hybridization, so it's going to be nonpolar. Everything cancels out. Steric number 6, it's octahedral, so you have 4 atoms in the equatorial and 1 in the axial at the top and bottom. Everything cancels out, nonpolar. Hybridization, sp3d2. If I throw in a lone pair, that's going to have to be at the axial, either the top or the bottom. When I do that, it looks like a square pyramid. Since I got one lone pair, it's going to be polar. sp3d2, still hybridization. Angles are going to be less than 90 because they're going to be pushing up. If I have two lone pairs, same hybridization. Angles are now going to be normal because the lone pairs cancel out each other. And it's going to be nonpolar because they're canceling out the dipoles. Suggest you learn these. Now I have some footnotes. They had some superscripts on that table. The 1 stood for the steric number, meaning that it equals the number of electron density regions. Single bond, double bond, triple bond, and lone pairs all equal 1 region. Angles are affected by the type of bonding. Electron density regions. Repelling forces are greater in lone pair, which is greater than lone pair, bonded pair, which is greater than bonded pair, bonded pair. And multiple bonds are greater than single bonds. Footnote 3, hybridization can be easily determined by the steric number and remembering the combined S1, P, maximum 3, and ND orbitals. Molecular geometry gives the shape of the atoms in the molecule. All we're looking at is the atoms. We're neglecting where the lone pairs are. We use that to determine the shape, but then we're only looking at what's there as atoms as what is the shape. Example sketch of electronic geometry around the central atom. And 6, the polarity is given in the case when all the ligands are the same. Insofar as geometry is concerned, a multiple bond acts as if it were a single bond. In other words, the extra electron pairs in the multiple bond, double or triple, have no effect on the geometry of the molecule, other than it has a slight effect on the angle. Insofar as hybridization is concerned, the extra electron pairs in the multiple bond are not located in the hybrid orbitals. According to the valence bond model, only one electron pair occupies one needed hybrid orbital for each bond, whether a single or multiple bond. So what we're saying here is there's one hybrid orbital involved in a multiple bond. The other ones, the double bond or the triple bonds, are not involved. So if I have a triple bond or double bond, one of those bonds in each one of those is going to be involved in that hybrid orbital. So one bond is hybridized. The other bonds are unhybridized. So 2 in the triple bond and 1 in the other double bond. For example, consider the molecule ethane. Each carbon atom is bonded to 3 other atoms in no lone pairs, which indicates the need for 3 sp2 hybrid orbitals, right? 3 electronic density regions means an sp2 hybridization, with 1 electron pair in each orbital. So what's happening here is you're going to have an sp2 overlap for your carbon hydrogen, an sp2 overlap here, sp2s overlap here, and an s2ps overlap for this other hydrogen. Then the carbon-carbon double bond, one of the bonds is an sp2 overlap with an sp2 overlap. The other bond is unhybridized. The third 2p orbital is left unhybridized and lies perpendicular to the plane of the trigonal sp2 hybrids. So that is a regular 2p, it hasn't been hybridized, regular 2p orbital. The following slide represents the sp2 hybridization of the carbon atoms. So what you have is your ground state. You have 2 electrons in the 2s, you get a 2p, you got 1 electron in 2 of the orbitals. What's going to happen? It's going to get excited, and this 1 electron is going to move up, okay, to the 2p. So you're going to have 1 2s and 2 2p orbitals form 3 sp2 hybrid orbitals, leaving 1 2p orbital unchanged. So this 1 electron is going to be promoted up. However, only 2 of the p orbitals and the 2s orbital are going to rearrange and form a sp2 hybridization. This other orbital will stay unchanged and be part of that double bond. So these 3, the 2s and 2 of the 2p's, form 3 identical sp2 hybrid orbitals. And then you still have that 2p unhybridized one by itself. To describe the multiple bonding in ethane, we must first distinguish between 2 kinds of bonds. You have a sigma bond, which is a head-to-head overlap of orbitals with a cylinder shape about the bond axis. This occurs when 2 s orbitals overlap or p orbitals overlap along their axis, hybridized. So we're looking at a carbon-carbon. We've got electrons being shared. We've got to look down the axis. We're calling the axis right here. If we have an overlap along that axis, that's called a sigma bond. It's a head-to-head overlap. A pi bond is a side-to-side overlap of parallel p orbitals, creating an electron distribution above and below the bond axis, unhybridized. So what you have here is a carbon-carbon situation. I have my axis, and we're saying the overlap is occurring above the axis. It's not occurring along the axis. So here's my overlap, and here's my overlap. It's not along the axis, while this is along the axis. So this is a head-to-head. This is a side-to-side. Okay, it's not along that axis. Okay, let's look at this. You got 2 hydrogens. If I figure out where the axis is, okay, it's right along here. You can see my overlap. It's along the axis. That's where my overlap is. So this is a head-to-head sigma bond. Look at the next one. Axis is right here. You can see once again, my overlap is along the x-axis. This is a head-to-head overlap and also a sigma bond. Last example, you can see here's my axis, and you can see my overlap is above the axis and below the axis. This is a side-to-side overlap and called a pi bond. 2 of the sp2 hybrid orbitals of each carbon overlap with the 1s orbitals of the hydrogens, and the remaining sp2 hybrid orbital on each carbon overlap to form sigma bonds. So this is that ethane example again. And what we're saying here is that you have sigma bonds occurring with your sp2 s overlaps. These are all based on your axial. Okay, so your overlap is along the axis. So you're going to have this along the axis and you got overlap. And along here, axis, axis. Those are all head-on overlaps. So what you have here is 1, 2, 3, 4, 5 sigma bonds. 5 sigma bonds. The remaining unhybridized 2p orbital on each of the carbon atoms overlap side to side, forming a pi bond. So what you have, you therefore describe the carbon double bond as 1 sigma bond and 1 pi bond. Here's your overlap here, above and below the axis. Okay, so those are pi bonds. Your pi overlap. So, your double bond involves a carbon-carbon bond, which is a sigma, which we just described on the previous slide, and then you have a pi bond, which your side overlaps with your carbon-carbon, which is unhybridized. Okay. The sigma bond is involved with hybridization. So ethane has 5 sigma bonds and 1 pi bond. So you got 1, 2, 3, 4, 5 sigmas and 1 pi. Bottom line, fairly simple. If you got a single bond, it's a sigma. It's a head-to-head overlap. If you got a double bond, one of those bonds is a sigma head-to-head, the other one is a pi, side to side. Triple bond, one of those sigmas are head-to-head, the other two are pi bonds, side to side overlaps. So, simply just learn this. Let's see if we understand. How many sigma and pi bonds does acetylene have? C2H2. Well, first off, you're going to have to draw the Lewis dot structure, right? If you draw the Lewis structure, you're going to come up with this arrangement where you have a single bond between carbon and hydrogen and a triple bond between carbon and carbon. Since the carbons have a steric number of 2, we know that we have a hybridization of sp on the carbons. Okay, so we have an sp overlap between this carbon and this hydrogen, and this carbon and this hydrogen, and then you have an sp overlap between the two carbons. This gives us 1 sp-sp head-on overlap for carbon-carbon and 2 sp head-on overlaps with hydrogen-carbon, giving us 3 sigma bonds. So you have a sigma bond between carbon and hydrogen, sigma bond between carbon and hydrogen, and a sigma bond between the two carbons. We also have 2 unhybridized side-on overlaps between carbon and carbon, giving us 2 pi bonds. That would be the other 2 bonds. Each one of those are a pi. So, this gives us a total of 3 sigmas and 2 pi's. 1 sigma, 2, 3 sigmas, and 2 pi's. Homework 68.